Now we look at a little bit more on the abstract Boolean algebras. In particular, we're looking at atoms and a basis for an abstract Boolean algebra. So again, remember what an abstract Boolean algebra is. We have different types, but it's just an algebraic structure. So that algebraic structure, you have some set. We can just call it B. And together, you also have to have a defined multiplication, a defined addition, and a defined complementation. Let me use this symbol for complementation. So multiplication, addition, and a complementation defined with a set. So together, it's an algebraic structure, which we just call an algebra for short, and it's an abstract Boolean algebra. In particular, we call it. So with this Boolean algebra, we know that we have 5 axioms that have to be satisfied under the definition for multiplication, addition, and complementation for the given set. So not everything can become an abstract Boolean algebra, but if it satisfies those axioms, so those are just rules, those are just laws that have to be satisfied within that set B, then it's called a abstract Boolean algebra. So we saw that in the last videos, different types that do satisfy whatever that definition of multiplication, addition, and complementation were for those elements in that set B. Okay, so let's just assume we have any of those abstract Boolean algebras. Let's come up with the atoms. So the atoms are an element in a Boolean algebra, and it will be called an atom if A is not the 0 element, so we don't want an atom to be the 0 element, anything other than the 0, and the second property has to hold. For every x in B, every x in the Boolean algebra set, either, this is supposed to be multiplication, but you don't have to write the multiplication symbol if you don't want to, it's understood. A times x is equal to A, or A times x is equal to 0. So if you look at that, you can always go back to sets if you're trying to visualize what this is, because Venn diagrams are nice to think about. So if I have A intersect, if I'm thinking about sets, remember in sets, we would have the power set, and then what would be your multiplication, addition, and complementation? What would they be defined as for that algebra, for that structure? The multiplication is defined as the intersection, addition is the union, complementation, you just negate that set. So this isn't a structure, it's an algebra. So what I could think of is if I have A times x needs to equal A, or A times x is equal to the 0 element. So with sets, you have some set A and you intersect it. So A would be the atom here, but you intersect it with another set, so X would represent maybe B. Then we need to get back A. So if you have A and B and you get back A, then A was contained within that other set B. So we're going to see that we're going to call these atoms building blocks. Or if you get back their intersection, if you think about sets again, A times X is equal to the 0 element. The 0 element for our power sets is the empty set. So it would be like saying A for our atom intersected with some element from the Boolean algebra that's a set, so I'll call it B, equals the empty set. So that's our 0, which means that they're going to be disjoint then. And also notice that we can think of this as for any x in any element in the Boolean algebra, if A is equal to A plus x, then the x must equal to A, or the x must equal the 0 element. So we know that in our property, A would equal A plus 0, so that's a given because of the Boolean identities. We know that's going to be true in any Boolean algebra. But then it says if you have A is equal to A or x, in order for this to be an atom, then this X here must have been A itself. So again, you're going to see that this is something called indecomposable. So A cannot be decomposed. You cannot form it from the sum of two other elements. It just basically stands on its own here. Okay, so again, we're just going to start with some Boolean algebra. And remember what a Boolean algebra is. An abstract Boolean algebra is just some set that you define what your elements look like. They could be, the power set. It could be just an n tuple. It could be a function. We even saw d sub 6. We'll look at that as well. And then you have some defined addition, multiplication, and complementation. Okay, so those are defined on that set, and they have to satisfy our axioms that we talked about in the other video. If they do satisfy, and that means they have to have a 0 element also, and they have to have a 1 element also, then it's an algebraic structure. It follows all the rules, so we can call it an algebra. So the atoms are the building blocks, and they are non-zero, so they're the non-zero building blocks of your Boolean algebra. And what that means is the atoms are said to generate, they create the algebra. So each element that is in your Boolean algebra will be able to be expressed uniquely as a sum of these atoms, of those building blocks. Now, except for the order of the atoms, because we know we have the commutative property, so you could just rearrange the order of those atoms, but you'd still have those same atoms being summed up, and it would be uniquely expressed except for the order. Now, atoms are disjoint, so what that means is if you had called two atoms A and B in your Boolean algebra, then either they're just the same atom, A equals B, or their product would have to be the 0 element. So you can think about sets again if you want to. Look at that. It just means that you don't have any overlap if you're thinking about sets, so they're disjoint. Now, atoms are indecomposable, which means that they're the smallest possible of these building blocks. And what you could think about is even, in fact, if you were trying to look at, say, B3, so order 3, then you can list, what would all of those elements in B sub 3 be? So remember with this one, it would be of order 3, and you list them as a 3 tuple, and it has the addition for the Boolean addition, and then it had defined multiplication for Boolean multiplication, and it had the complementation for Boolean complementation. So that's that algebra structure, where you just have to remember you're dealing with zeros and ones, and you have to do the addition as a Boolean addition, then Boolean multiplication, and the Boolean complement. So if I listed these, and what would they all look like? Well, you would list them out. It's the same as if you're trying to get all the possible bit strings of length 3, except for you just put commas in between, and you put the parentheses because it's an array now. It's listed as a 3 tuple. So let me just write out all the elements that would be in this set. I'm actually trying to write this out as a gray code, which we'll be talking about later, where I change just one entry at a time here. Okay, so I should have had 2 to the third, because the entries in B to the third, they can only be zeros and ones, but I have a 3 tuple. So I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. So this is going to be all of the possible elements in this set. So if you looked at that, what would be the building blocks? What would be those minimal elements that would generate all of the rest? Except, remember, it has to be non-zero to be our atom. So I'm just going to go ahead and cross out that 0 element. And remember, we did prove that that was the 0 element. It's easy to see that that's the 0 element in this structure. It satisfies all those properties for the 0 element in a Boolean algebra. Okay, so basically what I want is I want to look to see that I have to have a 1, so everything can differ just by a 0 or 1. That's the only entries for each of these. So a 1 in this last entry, and notice if I pick up a 1 in the middle entry and 0s elsewhere, and then a 1 in the front entry, first entry and 0s, those are going to be called the minimal building blocks. Those are the atoms of this set. So what's the reason there is, well, they can generate, first of all, they are non-zero, and they are also disjoint. So I needed those properties, but they can also generate the rest of the elements in this set. So for example, how would you get back that 3-tuple 0, 1, 0, 1, 1? Well, if I looked at adding, so in an array you just add like you do with a matrix component-wise. So what do you get back? You get 0, then 0 or 1, and then 1 or 0. So you get back that 1, the next one. And then, how would you get back this one? Well, again, the OR Boolean addition here, it would be, well, I have a 1 in the first entry and the second entry. So it looks like I would have to pick on this building block for the first entry, and then I would need this building block to get the second entry. So let me just write down that 1, 0, 0 plus 0, 1, 0. So I'm taking those two atoms, those two building blocks, and I'm using I'm using the operation of plus for this algebra, which is just the Boolean addition. So it's going to be, again, you do it entry-wise. So you do 1 or 0, and then 0 or 1, and then 0 or 0. See, and then you get back that entry. And you can do that for all of them. If you wanted to get back the 1, 1, 1, then what will you have to do? That's our 1 element, by the way, for this, B sub 3. If you wanted to get back 1, 1, 1, then I would take all 3 of those atoms and add them up. And they're all uniquely expressed this way. So if I took the 0, 0, 1, added it with the 0, 1, 0 atom, and then added it with the 1, 0, 0 atom, you will get back 0 or 1, 0 or 1 or 0, 1 or 0 or 0. Okay, there we go. So we get back that element. And you can do the last one. I just left off the last one. And they are written uniquely as the sum of atoms, except for, remember, I could have moved the ordering around because in a Boolean algebra, you have commutative property, so that order doesn't really matter. You're still going to get back the same output equals each of those. Okay, so the atoms are indecomposable, meaning I can't break them up further into other elements that are in that set. So the ones that I have boxed in are going to be our atoms for this abstract Boolean algebra, and they will generate all of the rest of the elements that are within that Boolean algebra. So we can think of atoms as the minimal non-zero elements. When I was saying smallest as possible, it's really thought of as the minimal, and again, non-zero, we have to remember that, elements of your Boolean algebra for those building blocks. So if you want to impose that word minimal, that means we need an ordering on our set. So what would be the underlying ordering of every Boolean algebra for a post set is defined by either this ordering, x plus y equals y, or x times y is equal to x for any two elements in your set. This is how we're going to define our ordering. So that's the underlying order. Now, if you have an underlying order, if you have a poset and you're talking about minimal elements, what do you think we could do there? Well, we could draw the Hasse diagram. So here's an example to list the atoms of the power set of S. And let's take S just to be the set A, B, and C so that we can stop our Hasse diagram here at some point. So remember what an atom is. The atom is going to be a non-zero element, and it has to satisfy condition 2 down here. For every x and b, either A times x is A or A times x is the zero element. So I've written down both sets so you can visualize what your choices are for the atoms. So I want to figure out the minimal building blocks here. If I draw the Hasse diagram, remember we're using this for our ordering. So we're going to say one element of our set is less than or equal to the other element if and only if x plus y is equal to y. So if I look at this, I'm going to start here at the zero element down below. Remember, that's the empty set. Now that can't be an atom, but I'm going to put the empty set, the zero element down below. And then I'm going to build this up, and I have set A, set B, and set C. So notice how this does satisfy this property that the empty set, so let me see if I can just squeeze it in here. I notice that the empty set is going to be less than or equal to, say, the set A. And if you plugged into this definition for the ordering, the x would be the empty set and the y would be the set A. So this is going to be if and only if. So let's see if this is true. If I plug in the empty set for x and I add my element y, which is the set A, do I get back y? Yes. When you do an or, the empty set or the set A, so remember in the power set, you're doing a union. So this really just means union here for that part. So you get back x plus y is equal to y. So that's why, this is how I'm getting the ordering. And you can do that for each of them, by the way. But we've seen this Hasse diagram, and this is how you draw it out here. So the zero elements down below, the one element appears up here on top. The minimal elements that are non-zero, so they're at the next level, will be your atoms. So your atoms here are A, the set A, the set B, and the set C. And then those are the ones that will generate everything above it. So it will generate this one, level on top, and then it will generate the level on top of that, the one element. Okay, here's an example with D, and this was supposed to be subscript 6. We call this D6, I believe. So here we have the set 1, 2, 3, 6, and we have addition, multiplication, and complementation defined differently. So this is different now when I think about my algebraic structure. The atoms here are going to be 2 and 3. Now, why do you think that's going to be? So remember, this is the set that you get to deal with. You have these elements, 1, 2, 3, and 6 as your choice. You know, those are your only choices here. It cannot be the zero element when you're talking about an atom. So remember what the zero element was? It was 1 was the set's zero element. So I'm going to have to throw out 1. So I know I'm not going to be dealing with 1 for an atom. And the one element, if you remember, is going to be the complement of that. So if I were to plug that in here, I plug in the zero element. So what is the complement of 1? The complement of 1 here is 6 over 1, which gives us back 6. Okay, but remember 1 was the zero element. So what I'm saying is zero's complement which would give me the one element, is equal to 6. So I've written the 0 element down here. I've written the 1 element up here. And then we have to look at the minimal element of this Hasse diagram. So again, this is the partial ordering. So I've actually applied this partial ordering to each of those. So how do I really know that, for example, 2 is less than 6? Well, I would just plug into this underlying ordering. So is 2 less than this 6 according to this ordering, if and only if x plus y is equal to y. So is x plus y equal to y? The x here I'm using as 2, the y I'm using as 6. So I'm going to plug in and say x plus y, and then I need to perform that operation. So what does 2 plus y mean? Oh, I'm sorry, let's go ahead and plug in 6 for y. What does 2 plus 6 mean to us? 2 plus 6, now this is not 8 because we're not on our normal algebra, we're on this algebra. So 2 plus 6 to us means to take the least common multiple. So I take the least common multiple of those two numbers to get my output. And what's the least common multiple of 2 and 6? The least common multiple is 6. So notice when you do 2 plus 6, so that means 2 plus 6 gives you back 6, which does mean x plus y equals y. So it does check. So I can say this is true. 2 is less than or equal to 6. So I can't, right away, it depends on what your algebra is. Not always is 2 going to be less than or equal to 6. We're just used to that when we're talking about our number line, our real numbers in that algebra system. But we have to always look at our structure and what it tells us to do in order to determine if one element is less than the other element. So if 2 is less than the 6, then it's going to be a level below in this example. I only have 1, 2, 3, 4 elements in this set. The 0 element is 1, the 1 element is 6, and here I'm left with 2 and 3 at the same level. Why is 2 and 3 at the same level? Well, can you get a relation out of the 2 and the 3? So notice, is 2 less than, which when I say less than, it's just ordering. Is 2 going to precede 3? Maybe that's a better word. Instead of saying less than, I'll say precede. Will 2 precede 3? Well, if and only if, you need to check. So you say if and only if x plus y is equal to y. So I just plug into the left-hand side. I plug in 2 for the x. I plug in 3 for the y, and I see what I get back. Now when I'm adding these, I'm not adding them like regular addition that we're used to in our math courses from high school. What I'm doing is I'm saying 2 plus 3 has to be the least common multiple. So what is the least common multiple of 2 and 3? Well, the least common multiple of 2 and 3 is actually going to be 6. So we had x, which was 2. We had y, which is 3. Did that give us back y? It did not give us back y. See, it did not give us back 3. So that means that 2 cannot precede 3. So if 2 does not precede 3, then they're at the same level. Okay, but they're the minimal values in the building blocks. So these are called the atoms. At this level, that is just one above the 0 element. Two and 3 are the atoms here. And now we talk about a basis. So a basis, this is just going to be given a Boolean algebra as set A of atoms of B, so these are just your atoms, is called a basis if every non-zero element of B can be written as a finite sum of atoms in A. So every non-zero element can be written as your finite sum of atoms in A. So you just want to make sure that you get all of your atoms from the set. So in fact, every finite, so it has to be finite, every finite Boolean algebra does have a basis. It's because we need that word finite because we need to have our finite sum of atoms. So for example, the finite Boolean algebras that do have, well, there are more, but I'm just giving you some examples. This is the power set, and I've restricted it, like we did before, to A, B, and C. So the power set with the union, intersection, and complementation. What were the atoms? The atoms were the set A, the set B, and the set C. So together, we just say they form a basis. So together, we say the basis will be this set of atoms. The difference is now for the basis, you're putting all of the atoms into a set. And together, if I use any of these atoms in this set, I can generate everything else in this Boolean algebra. And here's D sub 6 again. So notice the atoms were 2 and 3, and again they were not the zero element, and they were the minimal elements. So what we say is the basis is going to be the set of atoms, and we just write it in set notation and list them 2, 3. So they're not the zero element. The zero element was way down here, and they are the minimal building blocks that will generate everything above it. So you'll be able to generate 6 from the 2 and 3. And we saw that when we were trying to add them together, we got back 6. And then when I say add, what does that mean? The least common multiple. An example here, if we have an infinite Boolean algebra, we it's not going to have your basis here. So the atoms of the power set of the integers. So what does that mean? This means that you have all of the atoms to be, so if you look at the power set of, so it's going to be the power set of, and you're going to have all of these. Let me do negative, 1, 0, 1, 2, etc. So the atoms would be the minimal building blocks, which means that the atoms would look like this. Just your set n's where n is an integer. So if I were to list them separately, which you know you can't list them all, but it would be like negative 1, it would be 0, it would be 1, 2, and that's the problem, is because I can't list them all. It's not going to contain a basis. So if this is not finite, it's not going to contain a basis. And isomorphic. So here, a finite Boolean algebra having a basis consisting of n elements will be isomorphic to the Boolean algebra of the power set of I sub n. So what is I sub n? Those are subsets of, and then you just list the natural numbers. So it would be 1, 2, 3, etc. So it's the power set of the set of n, 1, 2, 3, all the way to n. So if you do have two finite Boolean algebras with bases of the same size, then I know that they're going to be isomorphic. Because remember, basis was that the generating, everything that can generate the rest besides the zero element. So that you're going to be able to map them to, you're going to have a nice mapping from one set to the next set. And also this says that the number of elements in a finite Boolean algebra cannot be more than the number of elements in your power set of I to the n. So that is a restriction for a finite Boolean algebra. If it's going to be isomorphic, if every finite Boolean algebra is isomorphic to this power set, then that restricts the number of elements that you can have in any Boolean algebra. It would have to be I guess 2 to the power n